In this video, we're going to be looking at one of the greatest applications of derivatives, and that is motion. And I usually tell my students I call it PVA. P for position, V for velocity, and A for acceleration. So what's the objective for this video? Well, we want to find the velocity or acceleration function given the position function. Sometimes we're going to ask you to find the acceleration given the velocity function. Another thing they'll ask is determine if a particle is speeding up or slowing down, whether I give you the position function or the velocity function graph, or I might give you the velocity graph. Determine when a particle stops or changes direction, if I give you the velocity graph. And finally, or I can also give you the velocity function too. Find the total distance traveled in an interval given the position function. And the last one here is the one where a lot of my students struggle with, finding the total distance of a particle on an interval if I give you the position function. Alright, so let's go ahead and look what position, velocity, and acceleration. What is position? Position is just merely, it's just the location. But on the location, most of the time we're going to be looking at the location at a number line. So for example, here's 0, here's 1, here's 2, here's 3. So if I said, what's my position of the particle? Well, you could say that my position there, x at 0, that means at 0 time, my particle is located at 2. And then later on, at 2 seconds later, we find out that my particle now is over here. So the particle traveled from here to here. So we're going to say that the position now is 0. Now, what is velocity? Well, velocity is going to be the change of distance over the change in time. So for this particle here, he was here and he traveled here, but he traveled over here in 2 seconds, but he traveled a distance of 2. So you could really say that his velocity is really 1 unit per 1 unit of time. All right, but velocity is known as the change in distance over the change in time. What I want to stress here is that velocity is always going to be some unit of measure of distance here over a measure of time. So for example, your velocity might be meters per second, it might be miles per hour, okay, but it's always going to be distance over time. Acceleration is the change in velocity over the change in time. So the units for acceleration is going to be something like miles per hour or hour squared. Okay, or you can say feet per second or second squared. Now here's the important part of the video today, and that is velocity is really just the derivative of position. So right here, this is my distance, and what I'm doing is I'm going to take the derivative of a distance with respect to time. So when I take the derivative of that, if you look at the video on related rates, you're going to find out that all you're doing is you're taking the derivative with respect to time, and that's all you're doing. So derivative is, velocity is the derivative of the position function. That's it. And acceleration is the derivative of the velocity. Okay, so how would I write that down? So now, what is the notation for position? The notation for position is going to be x of t or s of t. They have two of them, two very popular ones. Some books will go x of t and some books will go s of t. Now, when I say position, p, I'm talking of x of t or s of t. When I talk about velocity, I'm actually going to be looking at x prime of t or s prime of t. Now when I talk about acceleration is going to be v prime of t, or it can be x double prime of t or s double prime of t. So basically all I'm saying is that acceleration is the double derivative of position, or is the derivative of velocity. Okay, now here comes some important things that you need to know. All right, and do you see where I say PVA for my students? Position, velocity, acceleration. So to get from position to velocity, I take the derivative. To get from velocity to acceleration, I take the derivative. To get from position to acceleration, I take the derivative twice. All right. Now, motion is tested a lot on the AP exam, and it's going to be tested on my exam. So what are the things that you need to know for motion? All right. The position function tells us the location on the x-axis of the particle at any particular time, t. Okay. The velocity, when the velocity is zero, that means there is no change at all. So that means that the particle is not moving. Right? So when the velocity is zero, or they say when the particle is at rest, so this really means the particle is at rest. That's very popular on the AP exam. So particle at rest means that velocity is zero. That means the particle is not moving. Okay. When the velocity is positive, then they say that the particle is moving either to the right or up. Now, what do you mean by up? Well, rockets go up. Okay. Cars go to the right. Now, in the future, maybe cars will be able to go up, but in this case, right now, cars are going to the right and rockets go up. Now, if the velocity is negative, then they say that the particle is moving left or down. Okay. So down could be a drill going downwards, you know, excavators going down, while a car is moving left. Now, another very popular question in the last several years in the AP exam is a particle speeding up or slowing down? And what you need to understand is, if velocity and acceleration are the same sign, then you could say it's speeding up. It's like saying this: if I'm traveling to the right, but there's wind coming from the right, so there's wind, and I'm traveling to the right, the wind is going to speed me up. Now, if I'm going to the left, that means the velocity is negative, but my acceleration is to the left. Again, it's in the same direction, so I would say it's speeding up, speeding up. Now, if I'm going to the right, but the wind is blowing to the left, it's actually going to slow me down. Or if I'm traveling to the left, but the wind's going to the right, if you're ever ran against the wind, you know, if you're running against the wind and the wind is going opposite you, it's going to slow you down. All right. So if there are different signs, the velocity and acceleration are different signs, and it's said to be slowing down. Okay. So what we're going to do now is we're going to do some examples of motion. Okay. Now it says find the acceleration and velocity at t equals 1 when given the position function. Well, first we have to do is we have to find the velocity function. So the velocity function is going to be 2 minus 16. The acceleration function can be found to be a of t is going to be the derivative of this, so that means it's going to be negative 6. Now they're asking, what is my velocity at 1? Well, all I do now is substitute a 1 there. It's going to be 2 minus 6 times 1, and that's going to give me 2 minus 6, and it's going to be negative 4. And what does a negative velocity tell me? That it's traveling to the left, so it's going to the left. Okay. Now in this scenario here, my acceleration is negative 6, and believe it or not, when I ask for the acceleration of 1, students get stumped and says, hey sir, where do I plug in the 1? Well, there's no variable to plug it in, so that means that my acceleration is going to be negative 6. So that means that my acceleration is also going left. Well, if this guy is going left and this guy is going left, then you can honestly say that my particle, let's what? Is speeding up at t equals 1. And why am I saying that? Because velocity and acceleration at that particular time are both negative. Now, if one was positive and one was negative, then it would be slowing down. So let's look at another example. At what time t is the particle at rest if you're given the position function? Is the particle moving left or right at t equals 4? So what we're going to do is we're going to find, they want to know particle at rest. And this means velocity is going to equal to 0. So I need my velocity function. What's my velocity function? Well, the derivative of this is going to be 3t cubed over 3. So it's going to be, 3t squared. So it's going to be t squared plus 4t. Then I'm going to set it equal to 0, and I'm going to solve for t. So I'm going to factor out a t. So that means that the principal product of 0, if a times b is equal to 0, then one of them has to be 0. So that means that t is equal to 0 and t plus 4 has to equal to 0. So that means that at t equals 0 and t equals negative 4, the particle is at rest. Okay? Now, is the particle moving left or right at t equals 4? So we already have the velocity function. The velocity function is t squared plus 4t. So now what I'm going to do is I'm going to insert a 4. So v of 4 really means 4 squared plus 4 times 4, which is going to be 16 plus 16, and that's going to give me 32. Now, since it's positive, we're going to say that the particle is traveling to the right. If it was negative, it would be traveling to the left. All right? Let's try another example here. Find the total distance traveled from t equals 0 to t equals 4 if the position function is given as x of t is equal to 5t minus 4 minus t squared. Now, like I said, this is the one that gives my students trouble. So what you have to understand is you have to find the position of the particle. So you have to find the position of the particle at the beginning, find the position at the end, and then what you got to do is you got to find the position if it changes direction. So what I'm going to do is I'm going to make a little table here, and this is going to be t, and this is going to be my position at those important points. Now, what are my important points? The beginning and the end, and right here where it changes direction. Well, a particle is going to change direction when the velocity is going to equal to 0. So what I'm going to do is I'm going to find my velocity function. My velocity function is going to be 5 minus 2t. I set it equal to 0. 5 is going to equal to 2t. I divide by 2. I divide by 2. So that means that at t equals 5 halves, my particle is going to actually stop. It doesn't mean that it's going to change direction, but it's going to stop. So I'm just going to find the position at that time. So what is it that I do now? Well, I want to find the position at 0. What's my position at 0? So I take the 0 and I plug it into my position function, and that's going to give me 5 times 0 minus 4 minus 0 squared. And that's going to give me a position of negative 4. So my particle on the number line is at negative 4. So he's going to be negative 1, negative 2, negative 3, negative 4. So my particle is right there at t equals 0. So now at 5 halves, when the particle stops, where is he going to be located at? So I'm going to plug in a 5 halves in there. So that means I'm going to end up with 5 times 5 halves minus 4 minus 5 halves squared. And some of you are going to hate fractions. 25 halves minus, that's going to give me 25 fourths. So that's going to be 16 fourths minus 25 fourths. So what I'm going to do is I'm going to multiply this guy by 2, multiply by 2, multiply by 2. So I'm going to end up with 50 over 4 minus 16 over 4 minus 25 over 4. So that really means 50 minus 41. So that's going to give me 9 fourths. So that means that the particle is located at 2 and 1/4 is 2.25. So that means that he's going to be located at 2.25. So here's 1, here is 2, and here's 3. So there's 2.25 is going to be right there. So now the bug is there and there. Okay. So then I'm going to find the particle now at t equals 4. So I'm going to find my position. At 4. So when I plug it in, I'm going to get 5 times 4 minus 4 minus 4 squared. And that 16 minus 4 is negative 20, and 20 is going to give me 0. So now the particle is here. So let's see, the particle went from here to here, and then it went from here to here. And the mistake that my students will always do is they'll find the position at the beginning and at the end, and they'll say, oh, the distance from here to here is my answer, and it is not. You have to find the distance from here to here. So how much did I travel from negative 4 to 2.25? He actually traveled 6.25. Now, how much did he travel from here to here, from 2.25 to 0? He traveled 2.25. So if I add those up, we're going to say that the particle traveled a distance of 8.5. So that is my answer for this example. Okay? So be very careful on that. What about example number 4 here? It says, given the graph of the velocity function, okay, so I'm gonna put here velocity function. When does the particle change direction? So right here my velocity is negative, negative, negative. All of these are going to be negative. Why are they negative? Because they're below the x-axis. And right there, Mr. Quintana, the particle stops. So here it is at rest. That means my velocity is 0. There's a big fat 0 right there. That's the x-axis. Then it's positive, 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 positive. And some of you are going to say, sir, but right here is negative slope. I'm not asking for the slope. I'm looking for the location of the dots. The dots are above the x-axis. So when is the particle change direction? At t equals 3. So it changes at t equals 3. Because velocity changed from positive to negative. V of t changes from what? From negative to positive at that point. Okay. Now, when is the particle moving to the left from 0 to 6? Well, it's moving left from 0. Now 0 it's below, so I'm going to include it all the way to 3. Okay, so I'm not going to include the 3. Okay, because it's at rest at 3. Now the next question is the acceleration positive or negative at t equals 2? So right there they're asking, what is my acceleration? What's my acceleration at that point? Okay, that's the big question. So you got to ask yourself, I have acceleration, but I'm given velocity. What do I do velocity to get to acceleration? Well, I take the derivative. And the derivative is really the slope. So what's the slope right there? The slope is positive slope, right? So that means that is going to be positive acceleration. Now mathematicians don't like to say that. They like to say the derivative, acceleration, a of t, is going to be greater than 0. And that's it. That's the correct way of saying it. Okay. Now, right here my acceleration will be negative, and right here my acceleration is positive, and here my acceleration is negative. Okay. All right, let's look at the next example. This is the graph of my position function. What can you say about the sign of velocity and acceleration at t equals 4? So right there, they're asking for the velocity. What is my velocity right there? What is v of t? That's the question. So I'm at my position function. I'm at x of t, and I got to get to v of t, so I'm going to do the derivative of that. So that means that x prime of t, my slope right there, I make a tangent line, is going to be positive. It's going to be greater than 0. So that means that velocity is what? Is positive. Okay. Now the next one is my acceleration. So what is my acceleration? What is a of t there? All right, at t equals 4. So what you need to understand is that acceleration is x double prime of t, and the second derivative is really concavity. So I'm going to be looking at the concavity right there. So what kind of shape is that? We're going to say that that is N shape. So we're going to say that it's concave down. That means that a of 4 is less than what? 0. It's negative. And that's it. All right, we got, I believe, one more example. That is the last example that I'm going to do for motion. They want to know, this is the picture of velocity. Okay, is a particle speeding up or slowing down? Now, I'm going to be honest with you. I had a student who taught me this, and he said, when is the particle speeding up? Okay, or slowing down? Between J and K, between right here and right here. What's my particle doing? Well, right here, my velocity, right there, my velocity is positive. But my acceleration, meaning the slope there, is going to be less than 0. It's negative. So we're going to say that they're opposite signs, so it's going to be slowing down. And then some students were lost, and they say, hey, sir, what about over here? What about here? Well, right there, my velocity is less than 0, and my acceleration is less than 0, so it's speeding up. Okay? And then somebody over here, they're going to notice right there that my velocity is less than 0, but my acceleration is greater than 0. And we're going to say that it is slowing down. And in the first part right here, in this part right here, we're going to say my velocity is greater than 0 because it's above the x-axis, and my acceleration is greater than 0. So we're going to say that it's speeding up. So this is the correct way to define it. And one of my students say, sir, you're doing it way harder than that. And I'm going to say, what are you talking about? He says, right here, this is velocity. So this bar here means that my velocity is 0. It's 0. I'm going away from my velocity, so I'm speeding up. Then my velocity is going to change. Now I'm slowing down. I stop. I am speeding up because I'm going away from 0. And then I'm slowing down. And I'm going to tell you, that was one of my geniuses that I taught, one of the first years that I taught calculus. Okay? And that concludes the video on motion.